Hello everyone. As Marina already said, my research is based on the improvement in durability of conservation mortar containing barium hydroxide additive. The aim of the research is based to the issue that currently mortar have a shorter average life compared past mortar due to the more extreme weather phenomenon and due to the increase of nitric compound in the current pollution. And my idea was that through the use of barium hydroxide, I will be able to increase the durability of mortar, slowing down the mechanism of decay related to the nucleation of soluble salt, in particular sulfate salt, and the decay connected to acid rain. Before introducing you to all the tests and the analysis that I carry out for my research, I would like to explain first what is a conservation mortar. A conservation mortar is a material that conservatory use to structural repair or aesthetic reintegration for work of art, mostly outdoor and on inorganic material. Most of the time, conservation mortar must present the same physical features of the material on which are applied in order to don't create further deterioration to the original material. In other case, conservators prefer use mortar as a sacrificial material. That means that the mortar, in a kind of way, focus all the decay mechanisms focus on the mortar instead on the other material. In order to achieve a sacrificial mortar, the mortar has to be prepared with a higher level of porosity and permeability respect to the material on which is applied in order to be able to absorb all the water. The mortar must be less hard than the original material in order to be able to mitigate mechanical stress, but most of all be able to absorb vibration. And finally, last but not least, mortar must be workable. That means that it must be easy to use, present a good adhesion power, high plasticity in order to achieve the best result possible. The other character of my research is the barium hydroxide, so the additive that I use to prepare my mortars. Barium hydroxide is an inorganic chemical compound, is the hydrative form of barium oxide, and in Italy it was largely used during the 70s as a consolidator for limestone and in particular wall paintings due to the high reactivity with limestone substrate and in general carbon substrate. In general, barium compounds, in particular barium carbonate and barium hydroxide, share many chemical characteristics with calcium compounds. In particular, both of them are alkaline earth compound, but most of all, both of them are able to carbonate, as the reaction in the slide show here. And starting from that issue, I developed all my research because when I realized that barium hydroxide were able to carbonate exactly as carbon dioxide, I start to believe that it was possible to create a mortar with this kind of double binder, partially made of calcium carbonate as traditional mortar, but the other part made of barium carbonate. And it's exactly what I did in my preparation of the sample. For the preparation of the sample, I decided to do two groups of mortars, one with non-hydraulic mortar, so using a commercial putty, and the other part of mortar was made with natural hydraulic lime 3.5. That from my research with some conservator, I realized that this one was one of the most common used in conservation works in situ for monument, for architectural element. The preparation of the mortar was made using 3 different amounts of barium hydroxide, a lower amount, which was about a quarter, respect the amount of the lime, a medium quantity, which present half of the amount of lime in barium hydroxide, and equal amount of barium hydroxide and barium carbonate. And I repeat this proportion both for hydraulic and non-hydraulic mortar. Plus, I prepare also a group of sample, hydraulic and non-hydraulic, not presenting any additive, in order to have like control sample in which I can compare all my tests. After the preparation of the sample, I let them cure in these in ice trays, and I let them cool for about 3 months in a laboratory environment. So I use like, you can see here, doorbells, and then I was able to create a really particular environment with really high relative humidity, and then moving slowly through a more room temperature. After 3 months, my samples were ready for the research. And the first thing that I carried out was a study about the binder, in order to understand if the barium hydroxide that I used in preparation was able to carbonate perfectly with the rest of the mortar components. Unfortunately, during the preparation of the mortar, I carried out also the workability test, and I realized immediately that mortar containing medium and a large quantity in mortar, hydraulic mortar containing medium and large quantity of additive, they were not usable. So they completely failed the test, and considering that if a mortar is not workable, it cannot be used. And for this reason, I decided to exclude that two group of mortar from all my research. Coming back to mortar binder characterization, I decided to characterize the binder of all my mortar. I decided to use FTIR and XRD. And now we'll show you the result. Starting with hydraulic mortar, we can see that the spectrum of my mortar containing barium hydroxide, which is the purple one, and the control mortar without any additive, which is the red one, show a quite similar trend, with similar peak in the same wavelengths. But most of all, the main difference is about 800 centimeter -1, where we can see in the blue mortar, so the one with the additive, a peak, this particular peak, which corresponds to the presence of barium carbonate. Further confirm of the presence of the carbonation of barium hydroxide to barium carbonate was achieved using XRD, where we can see in the diffractogram on the right that together with calcite, hydraulic component, and quartz, we can also see peaks with W mark. That is correspond to whiterite, which is the mineral name for barium carbonate. Similar results are also visible for non-hydraulic mortar. In this case, we can see all the three samples with different proportion of barium hydroxide, and for all of them, we can easily recognize the peak about 350, which correspond to barium carbonate. Also in this case, further confirm arrives from the use of XRD, where we can see that all the mortar containing barium hydroxide present the W peak corresponding to whiterite, so barium carbonate. Even more interest for non-hydraulic mortar is that, considering that XRD is not just a qualitative analysis, but also a quantitative, the intensity of the peak gives us an information about the amount of compound of molecule in our sample. In this case, we can see for the mortar containing small quantity of barium hydroxide, the whiterite peak, so the barium carbonate peak, are really small because we use a little of additive. For mortar containing medium quantity of barium hydroxide, we can see that the peak increased their intensity, so the amount of material is bigger. And in particular, we can see that the whiterite peak is exactly half of the calcium carbonate peak, as we can say it in the preparation of the sample. And finally, for mortar containing equal amount of barium carbonate and of barium oxide and lime, we can see that whiterite peak and calcium carbonate peak are exactly the same. That is a really positive result, because in this way we have like an estimation that all the additive that we use in the preparation of the mortar carbonate well in our sample. After that, I test all my sample in order to understand if there was any physical change in the mortar. So if there were a change in the workability, hardness, porosity, acid raining spores, and acid raining exposure and salt exposure. As already said, from the workability test, non-hydraulic mortar containing large quantity of barium oxide didn't have a good result. So as we can see, they result non-acceptable in workability, about moldability, adhesion power, compactness, and making impossible their use in the plastic repair of this three-dimensional limestone. On the opposite, the non-hydraulic mortar result, all of them, all the three type of mortar result really good. In particular, the one with really small amount of additive. Another workability test was carried out about the repointing. So mortar was used to repoint area of this wall. And as we saw before for the other workability test for non-hydraulic mortar, the results are quite good. And in the worst case, the result acceptable. While for hydraulic mortar, in particular, the samples with large quantity of additive didn't show really good result. A further negative aspect that I found during the study is after curing, hydraulic mortar containing medium and large quantity of additive left this kind of white stain all around the worked area, and that was a further negative aspect that encouraged me to don't use this mortar for my study. After that, I decided to carry out an hardness test. As probably someone noticed from the picture of the preparation of the mortar, my sample were a quite small dimension in order to speed up the carbonation process. But unfortunately, this decision create a lot of problem regarding the choose of a method to measure the hardness of the sample. That's because typical instruments that are used in the measure of hardness for concrete and stone, for example, Smith hammer or durometer, were not designed to be used on such a small material. For this reason, I decided to use a rebound hardness measuring test for metal, which is the one visible in the picture there. Which was designed for small area, for small sample. And in this way, I was able to measure the hardness of my little samples. As you can see from the result, for non-hydraulic mortar, we can see that mortar containing small and medium amount of barium hydroxide additive present a quite similar hardness respect the control sample. We can see a kind of deviation, but in generally speaking, the average of the hardness result mostly the same. Completely different results show about the sample P1 containing really large quantity of barium hydroxide additive that it resolved so soft that it is not in the unit measure. So it was under the unit measure of our equipment because it was really, really, really soft. Completely different results are shown for hydraulic mortar, where the samples containing barium hydroxide additive result on the opposite, more harder respect the control sample. Considering that the hardness is always related to the porosity, I decided to carry out porosity investigation through the use of the scanning electron microscopy in order to be able to have an idea of the topography of my sample. And in this way, also be able to see the distribution, measure shape of the porosity. Starting with the hydraulic mortar, we can see that the main difference between mortar containing barium hydroxide and mortar not containing barium hydroxide is that the additive decrease a lot the amount of capillaries in our mortar, and that is a quite interesting result, considering that hydraulic mortar, the definition of barium of hydraulic mortar is mortar with really small pores. So that is a quite important change. The other important change in hydraulic mortar that we can see in relation to the use of barium hydroxide is the change in porosity in the group of pores between 300 and 2000, which are the sorption pore, and they are the pore that usually are used by the material to transport liquid water. And that is really interesting because that pore are directly correlated with the permeability of the mortar, and usually the hydraulic mortar are mortar with a really low porosity. And in this case, we can start to believe that mortar containing barium hydroxide probably have a better permeability respect traditional mortar. Same study was made for non-hydraulic mortar, and quite surprisingly, results are completely different in respect to hydraulic mortar. In this case, we can see that the use of barium hydroxide increased terribly the amount of capillaries, So we can see that mortar without barium hydroxide have a quantity of capillaries quite reduced, while the mortar containing the barium hydroxide has much more capillaries. But even more interesting is the changes in the really, really large pores, where mortar containing really large quantities of barium hydroxide present huge amount of really, really large pores. That is a really strange result, considering that that kind of pores are strictly involved in the density of the mortar. That means that our mortar containing large quantity of barium hydroxide will be much less dense in compare with the same mortar without barium hydroxide. And in a kind of way, that can also explain the really strange result that we had for mortar containing large quantity of barium hydroxide related to hardness, in where the mortar was so soft that it was impossible to be measured. In that respect, I decided to do further research about the porosity of the mortar through the study of the hygroscopic weight. That is a physical concept based on the Archimedes principle. It's a really easy way to estimate the percentage of porosity of material, in which you have to carry out just three measures. The first one is the measure of the sample as dry. The second one is the measure of the sample immersed in the water, also called hygroscopic weight. And the third measure is the measure of your sample out to the water, but completely saturating water. Once you have the three measure, you can start to calculate the apparent and real density. And after that, you are able to estimate the percentage of porosity of your material. In the case of the hydraulic mortar, we can see that even if the distribution of porosity is quite changed in relation to the use of barium hydroxide, the final percentage of porosity of the two mortar is exactly the same, and that is a quite positive result. On the opposite, the result related to non-hydraulic mortar showed that the amount of porosity, so the percentage of porosity, increased directly with the amount of barium hydroxide used for the preparation of the mortar. As I said in the beginning, usually when mortar are used as a sacrificial material, present higher level of porosity can be considered as something good. But in this case, in particular for mortar presenting medium quantity of additive and mortar containing large quantity of additive, the increase of porosity is too high, and that's considered as something negative because the mortar it's weak in this way. Finally, I carry out a study in permeability through the calculation of the water absorption in different timing, and the sorptivity. The sorptivity is the amount of water absorbed by a porous material just through the pores, just through the capillaries, so the really small pores. And those results gave me an idea about how the material is able to absorb water. And quite surprisingly, I realized that hydraulic mortar containing barium hydroxide are able to absorb less water in comparison with mortar containing mortar without any additive, and that was quite surprising because from my STEM study, the surface pore were much more in mortar containing additive. But even more surprising and also more positive result was about the sorptivity, where we can see that the orange line, so the mortar containing barium hydroxide, it's able to absorb less water through the pores. That is a really positive result in relation to hydraulic mortar, because usually one of the negative characteristics of this type of mortar is that they are mechanically weak, because often the nucleation of salt in the capillaries create a lot of disruption in the material. In this way, if the material is less able to absorb water through the capillaries, that kind of decay mechanism can be mitigated. Completely different results are shown for the non-hydraulic mortar, where with the increase of barium hydroxide additive increase also the ability of the mortar to absorb water. And quite surprisingly, the sorptivity is not changed for any of the sample containing barium hydroxide. Finally, I realized my accelerating aging test for the decay mechanism. I started with the acid rain exposure, where I designed an aging cycle where I was able to reproduce 3 years of rain exposure of the mortar in about 10 days. Using an acidic water solution having pH about 4.5, made of sulfuric acid mixed with nitric acid. And as we can see, for mortar not containing barium hydroxide, the interaction with the acidic solution create for the initial part a constant and then a really sudden losing in weight. That is due because the acid solution is able to erode the line boundary of our mortar. Completely different is the result of our hydraulic sample containing barium hydroxide, because as we can see, the trend of the losing weight it's reaching up and down. That is due to the formation of barium sulfate. Barium sulfate is the deterioration product of the reaction of barium carbonate with sodium with a sulfuric solution. And its formation is really interesting because differently from the decay product from calcium carbonate, which is calcium sulfate that is highly soluble in water, barium sulfate is completely insoluble in water. So its formation corresponds to a new material that is no more soluble in water, creating in a kind of way an increase in weight. Similar result is also visible for non-hydraulic mortar. For our sample without any additive, the trend of the losing weight is constant, and the material lost is quite a lot. While for our mortar containing barium hydroxide, we can see that the trend is not it's reaching up and down. And finally, due to the formation of barium sulfate, we have a much less losing weight. The final test that I carried out was about the assessment of the salt exposure. I decided to put my mortar sample in half cover with a solution of a saturated solution of sodium sulfate salt. And as you can see from the photographic record, but most well from the graph, sample containing no barium hydroxide after the second cycle has a terrible disruption of the material due to the formation of the soluble salt in the lattice of the mortar. And that is particularly visible in the graph, but most of all, it's visible in the picture, where in the first cycles of impregnation, mortar not containing barium hydroxide are completely destruct, while mortar containing barium hydroxide present a much better shape. Same result is visible also for non-hydraulic mortar, where it's even more evident because we have more samples, and we can see that for PX, so the sample that doesn't contain any barium hydroxide, after 4 cycles, my samples were completely destroyed. While moving through measure addition of additive, we can see that the material is in a better condition. This is again due to the formation of barium sulfate, so barite, which is insoluble and allowed salt to don't interact with the lime, but interact with the barium. That is the summary of the result of all my tests, and we can see that overall, mortar containing smaller quantity of barium hydroxide were the ones that had the better overall results. So the result ideal for the workability, their hardness, porosity, and permeability remain the same or increase respect mortar not containing barium hydroxide, and the resistance about acid rain and salt increase a lot. About mortar, the non-hydraulic mortar containing medium and large quantity of barium hydroxide, even if overall the results were not too negative, they can be considered acceptable for any conservation treatment, that because in particular regarding the porosity and the hardness, the change from the traditional mortar is too different, and the material is considered too weak to be used in any conservation, in real conservation treatment. After all the scientific experimentation, I decided to use one of the barium hydroxide mortar, in particular an hydraulic mortar containing small quantity of barium hydroxide in a real conservation treatment. And in particular, I use it for the restoration of one of the door case of Sitting Hills of London Art School. And that is a picture of before and after treatment. And the reason of my decision was mostly related to create a real case study in order to be able to check in long term how the barium hydroxide mortar is able to decay. So at this purpose, I create this form that I left to Sitting Hills of London Art School, and it can be used by future students, which can do an assess every year, can do an assessment of the door case, checking how the mortar that I use can decay, is decaying in relation to a small area that I repaired using instead normal mortar. And that's all the aspects that they have to consider and evaluating. In conclusion, I can say that I confirm that the chemical compatibilities and similarities between barium hydroxide and calcium hydroxide make the creation of barium hydroxide mortar possible. And the most important achievement is that the formation of barium sulfate in mortar containing barium hydroxide is extremely positive, because allowed a better resistance to any water sulfur decay mechanism. So in this case, it's formation of salt and acid rain. Another positive result that I was able to achieve through this research is that, in particular for hydraulic mortar, the use of barium hydroxide helped to mitigate that characteristic that usually are considered negative about this type of material. In particular, the low porosity and the low porosity and permeability, that through the use of barium hydroxide, they are slightly mitigated, making that type of mortar more resistant to not just to salt and acid rain, but also more generally to any type of mechanical damage. That is my research, and I would like to thank you most of all Jennifer, who supported me in the execution of the research. I want also to thank you Marina and Tracy, Katrina that is not here today, but she helped me to write the research, and also the laboratory that support me in the analytical part of the research, in particular UCL Archaeology Department and the Imperial College, and finally also the Porosity, which is the business that support me in the use of the hardness equipment. And thank you to all of you for your time.
Thank you so much, Jessica. So, any questions?
Jessica, that was brilliant. Thank you very much. So from your results, where would you, if somebody were to come to you and say, you have tested this material very thoroughly, what would you see as the most useful way of using mortars with barium hydroxide as an additive going forward? What situations would be most beneficial?
At the moment, I believe that the best way to use barium hydroxide mortar is for outdoor treatment. So I strongly suggest to use non-hydraulic mortar mixed with barium hydroxide with small quantity. First of all, because it's the one that I tested in a real conservation treatment, but also because rarely non-hydraulic mortar are used without any hydraulic additive, and I didn't have time to test that possible adding in this. I don't feel confident to suggest to use it without any any tests before. So personally, I think that use for a door treatment, hydraulic mortar with barium hydroxide can be a valuable conservation project.
Thank you.
Thank you.
Any more questions? I've got a suggestion. I think apart from obviously publication of results, which you're supposed to do as a May student, I would suggest I invited Heather, head of carving department, but she is a building conservator on top of being a carver. So I would suggest, because she couldn't join us, I would suggest to send her a copy of your dissertation, because I think it would be very valuable and interesting to build to conservators in building conservation.
Okay, thank you.